Okay, let's jump in. Look up at the night sky tonight, just for a moment.
Mm-hmm.
What do you feel? Is it wonder,
Yeah.
curiosity, that deep-seated human drive to know what's out there?
Yeah, that pull.
That feeling, that enduring fascination with space exploration, it's powerful. It fuels dreams of new worlds, incredible technology, maybe even, a fresh start for humanity.
Definitely dreams.
But getting there, staying there, the reality is a whole different story. It's brutal.
It absolutely is. The romance of space is one thing, but the nuts and bolts, the sheer unforgiving difficulty of it, biologically, psychologically, technologically,
Right.
it's immense. It
Right.
challenges us on every single level.
And that's the core tension we're exploring in this deep dive. We're unpacking that fundamental conflict, the powerful why driving us outwards versus the staggering how of actually getting there and surviving.
Exactly.
Our roadmap for this comes from a fascinating source,
Mm.
an educational guide created to go with the IMAX film Destiny in Space.
Oh,
Yeah, it's full of information about exploring space, designed for teachers, but it gives us a fantastic framework for understanding the immense hurdles humanity faces, among the stars.
right, a good foundation. Our mission today, then, is to sort of extract the essential nuggets of knowledge from this guide for you. We'll look at the deep-seated reasons why we go, what space does to the human body and mind, and the incredible tools we've built to overcome those challenges.
So let's start there. Why do we go? This guide points out that exploration isn't just some individual quest for glory. It's a massive cultural endeavor.
Yeah, it's collective.
The decisions to push into space are incredibly complex, involving huge debates about how we spend global resources, influenced by everything from the economy and politics to, well, competing needs right here on Earth.
And what's really interesting, I think, is how resource limitations have perhaps unexpectedly fostered international cooperation.
How so?
Well, before the 1970s, the space race felt very much like a competition between nations.
Right, U.S. versus Soviet Union.
Exactly. But as the scale and cost of space exploration grew, countries started working together, sort of out of necessity.
Makes sense.
You see this today with global use of sophisticated orbiting telescopes and multinational crews living and working together on the International Space Station. It's a shared challenge that often transcends national boundaries.
And this drive has a multi-generational reach, doesn't it? The guide highlights how it connects us across time.
It really does.
Think about the scientists who worked on the Voyager probes decades ago, seeing their own children later become scientists, interpreting data from those very same spacecraft.
Wow, yeah.
Or the image of 3 generations of a family watching the Hubble Space Telescope launch. It truly builds on the past while preparing for the future.
So this material, it outlines several powerful motives driving this monumental effort. One of the most compelling, perhaps controversial, is the idea of colonization.
Right, the big one.
This is about more than just setting up a base, It's the dream of new beginnings, a chance to maybe improve on the mistakes of the past, create entirely new cultures and societies.
The first start.
Yeah, and it also comes with the idea of increasing our understanding of Earth's unique and fragile place in the cosmos. And for some, it's even seen as a potential escape valve or fallback location in case of, global catastrophe here.
Okay, beyond the practical, there's the raw pull of the frontier and curiosity.
Mm-hmm. Because it's their feeling.
It's that fundamental human desire to explore simply because we can. The idea that society shouldn't be limited to just one planet. There's a sense that future generations would look back and perhaps judge us for not using the incredible technology and creativity we possess to venture outwards.
Right.
Space is presented as the ultimate unbound frontier.
And as we touched on, the act of international cooperation itself becomes a significant motive.
Yeah, that's interesting.
Bringing nations together through a common, incredibly difficult goal, much like the collaborative efforts in Antarctica, actively helps break down cultural barriers and fosters global relationships.
Okay. And finally, there's the profound search for life.
Ah, yes. Always fascinating.
This isn't just fodder for science fiction, is it? The potential discovery of other intelligent forms and the possibility of learning from them and them from us is a huge driver.
Definitely. The guide notes that we often learn most about ourselves by studying others.
Mm-hmm.
And finding life elsewhere, or conversely, discovering that we are completely alone in the universe, I mean, that would fundamentally change our understanding of everything.
Yeah, profound implications either way.
So you see, these motives aren't just abstract thoughts. They represent a complex mix of deeply ingrained human desires, practical concerns, and visionary aspirations that underpin the massive investment required to leave our home planet.
But realizing these dreams, that's where the brutal reality kicks in, like you said.
Exactly. That's the hard part.
Because going into space isn't just about why you go. It's about how incredibly difficult it is to keep a human alive and functioning there. Simple actions that are second nature here become monumental challenges, just trying to manipulate tools, for instance.
Right. That's why the training is so extensive. Astronauts spend hours underwater to simulate weightlessness.
Right, in those big tools.
Practicing everything from spacewalks to using robotic arms while wearing bulky suits and gloves. It's like trying to do delicate surgery while wearing boxing gloves in a swimming pool. It's just awkward.
Wow. And the long-term effects are serious, too. A hypothetical one-way trip to Mars. Maybe 9 months, you said?
Around that, yeah. The guide mentions cosmonauts who spent a year in orbit came back with significant loss of muscle and bone mass, struggling to even walk initially.
That's intense.
This points to a fundamental problem. Our bodies evolved for gravity, so how do you counter that when there is none?
Good question.
One potential solution discussed is generating artificial gravity by spinning the spacecraft.
Okay, we'll come back to that. But it's not just the big physical stuff, right? Your senses get completely confused. Keeping your balance, for example.
Oh, yeah, absolutely. Here on Earth, it's this continuous symphony between nerves in your muscles and joints telling your brain where you are, your vision providing visual cues, and your inner ear.
The inner ear.
Specifically, those fluid-filled semicircular canals that detect head rotation.
How do they work again?
Well, that fluid lags behind when your head turns, bending tiny hair cells like microscopic reeds, which signals your brain you're rotating.
Okay.
In weightlessness, that whole system goes haywire. Your eyes might see that you're perfectly still relative to the cabin walls, but your inner ear isn't getting any of those familiar gravity cues or fluid shifts.
Ah, so they disagree.
Exactly. The sensory conflict is the most accepted explanation for space motion sickness. Astronauts are rigorously tested for their response to this, spinning chairs, balancing tests with eyes closed, all that.
Right.
Your eye reflexes are involved too. One tracks slow movement, while a quicker one linked to the inner ear helps keep your eyes stable when your head moves. It's basically a system built for Earth that just doesn't work right in space.
Fascinating. And then there are the psychological challenges, that what the source calls the faraway feelings.
Isolation, separation from everything familiar on Earth, particularly on long missions.
Yeah.
Leaving your cultural comfort zone, the familiar people, sights, sounds, even smells, causes emotional unrest. The guide notes it's surprisingly hard to predict exactly what you'll miss most.
Really?
Yeah, even simple things like your sense of taste can change in space. Personal items become hugely important anchor points, as does the act of documenting your experiences, keeping journals and such.
And think about the sheer confinement, too. Living in cramped quarters, often sharing sleeping spaces with limited privacy.
Absolutely. Crew compatibility becomes absolutely critical for mission success and, well, sanity.
I can imagine. And then there are the communication delays. A message to Mars can take anywhere from 4 to 20 minutes one way.
Yeah, that delay is a killer for conversation.
Imagine trying to troubleshoot a critical mission crisis, or even just have a normal chat, when every exchange involves maybe a half-hour round-trip delay.
Right. Real-time back and forth is impossible. Only with the crew right there with you. NASA's Human Factors program dedicates significant effort to studying these complex psychosocial issues. Authority structures, isolation, sleep deprivation, environmental factors, crew emotions. It's a whole field.
Wow. And of course, just simply living requires bringing everything with you. You can take it with you, as the material puts it.
Everything. Water is especially critical. Earth's abundance of liquid water on its surface is incredibly rare, cosmically speaking.
So on a spacecraft, water isn't disposable. It's constantly treated and reused.
Exactly. Mimicking Earth's own water cycle on a microscale. Very closed loop.
Which brings us to food, the idea of gardening in space.
Growing your own salad. Researchers at Kennedy Space Center have been testing hydroponics in sealed rooms, essentially creating closed-loop systems where plants can grow without soil.
What are the benefits there, besides food?
Well, plants offer several benefits. They absorb CO2, produce oxygen, provide opportunities for scientific experiments, obviously yield food, and even offer crew members a psychological boost through, like, recreational gardening.
A bit of green helps.
It does. But there are risks. Plants can produce unexpected gases, maybe harmful ones, and if they die, you not only lose a potential food source, but also potentially an oxygen source.
Right, double whammy.
So the ideal space plants are tough, compact, tasty, nutritious, easy to pollinate, have short growth cycles, and seeds that are easy to handle.
Any examples?
The guide mentions lettuce, wheat, soybeans, potatoes, and rice have been tested. Algae technically meets many requirements, but apparently isn't very pleasant to eat.
Yeah, probably not. And soil. You mentioned no soil.
Too heavy, too bulky. Researchers are looking into alternative growing media like plant watering crystals that expand when wet and compact when dry.
Clever.
And plants don't eat soil anyway. They photosynthesize and need minerals provided by fertilizer, so a hydroponic fertilizer is required.
And watering. Must be tricky without gravity.
Very tricky. Leading to research into things like agar gels, vacuum pots, and porous ceramic tubes to deliver water carefully.
Okay, what about animals?
The source clarifies that animals, if they went to space, would be for experiments or perhaps companionship, but not as a food source.
Why not?
They simply require too much food themselves to be efficient protein sources on a long mission. Takes too much resource.
Got it.
Experiments conducted in orbit, like those by Norman Thagard and Roberta Bondar, help us understand how plants respond to microgravity. Clinostats are used on Earth, too, to simulate some effects.
And speaking of gravity, or lack thereof, measuring mass in weightlessness is different, right? You can't use a standard scale.
Nope, useless. Instead, you use a device like a swinging chair. The period of the swing tells you the mass. The more massive, the slower it swings back and forth. Tamara Jernigan is given as an example of someone who used this.
Huh, ingenious. So you see, keeping humans alive and functioning is a monumental task, just packed with biological and psychological hurdles.
It really is.
This is where the technology we build comes in. The tools and tech that let us bridge that gap between our fragile bodies and the harshness of space. Think about the relationship between humans and robots. The Apollo 11 moon landing, that ultimate human achievement, was preceded by robotic scouts gathering data.
Absolutely. Robots pave the way, assessing environments and collecting data before humans arrive, or sometimes instead of humans arriving.
And robots aren't just the humanoid figures you might see in science fiction.
Not at all. As the guide notes, they're simply machines designed for specific tasks, whether that's stripping paint, answering your phone, or operating in environments too dangerous or difficult for humans.
What kind of tasks?
Well, they perform long-term passive tasks, like seismic monitoring, handle repetitive work like construction, deal with hazardous materials like toxic spills or radiation, and explore extreme environments like volcanoes, deep ocean trenches, or, of course, other planets.
Robotic spacecraft are extensions across the solar system, flying by, orbiting, landing.
Right.
They map, see things our eyes can't, and analyze materials we can't touch.
Exactly. Think of Venera 17 surviving for just over 2 hours on the surface of Venus before succumbing to the intense heat and pressure.
Incredible it lasted that long.
Or Voyager enduring Jupiter's crushing radiation belts. The Viking landers sending back crucial data from Mars that showed no organic life but clear evidence of past water.
Game changer, that water evidence.
Or Magellan mapping Venus using radar right through its thick clouds. And of course, the Hubble Space Telescope giving us those breathtaking views of the universe.
The robots definitely have advantages.
Oh, big ones. No return trip necessary, no expensive life support systems required.
But they have challenges too. Intricate programming is a must. The guide mentions an activity simulating how something as simple as turning requires a complex sequence of instructions.
Yeah, it's not trivial. And signal delays over vast distances are a huge factor. That 4 to 20-minute delay to Mars means a rover exploring the surface might have to sit idle, waiting for instructions from Earth if it encounters an unexpected obstacle.
So it can't just react instantly.
Not if it needs input from Earth. This raises a fascinating question. How much independence can we actually build into these machines? How smart can we make them?
And advances are constantly increasing their autonomy, right? Onboard computers are getting smarter.
Definitely. Helping robots navigate complex terrain without constant human oversight. They're becoming more capable explorers in their own right.
Okay, shifting gears slightly. Our ability to see beyond Earth also relies heavily on technology, our telescopic eyes.
Crucial technology. Most of what we know about the universe comes from capturing and analyzing light across the entire electromagnetic spectrum, gamma, X-ray, UV, visible, infrared, radio, all of it.
The problem is Earth's atmosphere, which protects us, also blocks most of that light.
Yeah, thankfully for life, but frustrating for astronomers.
Right.
Especially the shorter wavelengths like X-rays and gamma rays. Only visible light, some infrared, and radio waves get through relatively well.
And even the light that does penetrate the atmosphere is affected by disturbances. Turbulence bends light.
Making stars twinkle or creating those hazy heat waves you see over hot pavement.
Clouds and mist dim or completely block the view. And foreground light from the moon or city lights drastically reduces contrast.
Big time. You know how many more stars you see from the dark countryside compared to a city? That's foreground light pollution, washing everything out.
That's why ground telescopes were strategically placed to minimize these issues on high mountains for clearer air,
Less atmosphere above you.
in dry climates for infrared, and far from cities for radio telescopes like those used by SETI, searching for signals from other civilizations.
Right. But space telescopes like Skylab, IRS, and Hubble are the ultimate solution. They are above the atmosphere, acting as the ultimate mountaintop, collecting any type of light without distortion or blockage.
They give unique views.
Unparalleled views. Skylab gave us incredible views of the sun in different wavelengths. IRAs discovered thousands of previously unseen infrared objects. And Hubble, well, Hubble continues to revolutionize our understanding of the cosmos.
Amazing tools. Going back to the human body's struggle with weightlessness for a sec, we mentioned the idea of spinning spacecraft to create artificial gravity.
Right, to counter muscle and bone loss. The guide explains how spinning a craft provides a gravity-like force, an inertial or centrifugal force, really.
How does that work? Like practically?
Think about demonstrating this with something like a salad spinner and some dice. When you spin it fast enough, the dice cling to the sides.
Okay.
On Earth, that's the outward inertial force overcoming Earth's gravity pulling them down. In space, with no Earth gravity, that spinning force creates a simulated gravity pulling you towards the outer wall.
So the faster you spin or the bigger the radius?
The stronger the effect. The speed needed depends on the radius of the spin. Designs range from the iconic ring station in 2001, a space odyssey, to more realistic proposals involving, say, tethered modules spinning around a central hub.
Still feels pretty sci-fi, but maybe necessary.
Potentially for very long duration missions.
Finally, we have to talk about the incredible protective layer that allows humans to step outside the spacecraft at all. Suiting up for space.
The personal spacecraft.
Because the space environment is instantly lethal. Vacuum, extreme temperatures, dangerous radiation, micrometeoroids.
Wow.
Just awful.
Absolutely deadly. A spacesuit is essentially a personalized miniature spacecraft for extravehicular activity, or EVA. Its functions are absolutely critical, protecting the astronaut from radiation, the vacuum.
Meaning no oxygen, no pressure.
Right. Protecting them from the extreme swings in temperature, from searing sun to freezing shadow, and potential impacts from tiny high-speed particles of space debris.
They look bulky, but they're incredibly complex, multi-layered.
They are. Many thin layers are more effective against puncture than a single thick one, and they also provide crucial thermal insulation. You've got an inner pressure bladder, a restraining layer to keep it from ballooning out.
Like a tire.
Sort of, yeah. Then thermal and puncture-resistant layers. A hard upper torso shell, the helmet with its protective visors clear and gold ones usually, and the gloves. Fiercely difficult to work in, hand fatigue is a real problem.
I've heard that.
And the life support system backpack is vital. It regulates temperature, provides the pure oxygen the astronaut breathes, removes the carbon dioxide they exhale, and maintains the internal pressure of the suit.
And they breathe pure oxygen.
Pure oxygen, but at a lower pressure than Earth or the shuttle cabin. This is essential. If the suit were inflated to Earth's normal atmospheric pressure, it would become so rigid it would be basically impossible to move in.
Like a balloon man.
Pretty much. The suit even has a built-in snack and water supply and crucial communication systems. EVAs can last for 7 or 8 hours.
Wow, a long workday. And for movement outside the craft, there's the Manned Maneuvering Unit, or MMU.
Yeah, that backpack with gas thrusters for flying around untethered, although they use tethers more often now. Suits have evolved over time, adding more layers, becoming more sophisticated. The guide notes that future, more rigid suits might allow for higher internal pressure, making them maybe slightly less rigid or easier to work in.
And it's interesting that some ideas for spacesuit design were borrowed from deep-sea diving suits.
Makes sense, right. Given the similar challenges of dealing with extreme pressure differences, whether it's high pressure in the deep sea or the near vacuum of space, similar engineering problems.
So you can really see how these pieces fit together. We have the powerful, multifaceted motives driving us outwards,
So why?
confronting the incredibly tough biological and psychological realities of putting fragile humans into an utterly alien environment.
How difficult.
And the ingenious technology we develop, from robots that explore where we can't, to telescopes that show us the universe, to the suits that literally hold us together in the vacuum that allows us to even contemplate the journey.
Yeah, it's that interplay between the dream, the harsh reality, and the tools we create.
These are the fundamental factors, the deep-seated desires clashing with the immense practicalities that are shaping our journey into the cosmos. And it leaves us with a powerful thought to carry with us. Given the absolutely incredible capabilities of our robotic explorers and space telescopes, I mean, they can see things we'll never see, go places we could never survive, analyze environments we can only dream of experiencing directly.
They're amazing proxies.
Will humanity ultimately be satisfied to explore the universe primarily through the eyes of the machines we create? Or is the direct human presence, the act of being there, feeling it, seeing it with our own eyes, an absolutely essential, irreplaceable part of our destiny among the stars?
That's the big question, isn't it? Something for you to really think about the next time you look up at that night sky.